Okay, continuing with section 1.8, this is the last video. We have a couple of examples here. So the example number 6 says, show that the t defined by this rule is not linear. So in this case, we have to show that the transformation is not linear. So we want to see if it satisfies the properties of linearity. So we check the first one. But before I start doing the problem, notice that the way the vector is given here is a little bit different. So normally we have been using column vectors. So if a vector x having coordinates x1, x2, we write them like this vertically, but here they are written in parentheses. So this is another way of writing vectors. We use parentheses and put them in a horizontal form with the comma in between and parentheses around it. Also note that this could be considered as the endpoints of the or the terminal points of the vector on the R2 in the R2 plane. So we want to check the first property of linearity, which says the t of x plus y. So if you have two vectors x and y, then you add them and take the transform, then the result should be sum of the transform of the two vectors. So it should be t of x plus t of y. So we want to check if this transform satisfies this property. But before we start it, let's figure out what the coordinates are going to look like. So if the coordinates of x are x1, y1, x1, x2, and the coordinates of y are y1, y2, we are going to add them. So we end up getting x1 plus y1. So the first coordinate of the x plus y vector is x1 plus y1, and the second coordinate is x2 plus y2. So this is x plus y. So now I apply the transform on it. So t of x1, x plus y will be equal to, according to the transform, it should be the first coordinate, which is going to be x1 plus y1, minus 2 times the absolute value of the second coordinate. So it will be 2 times absolute value of x2 plus y2, comma. The second coordinate is the first coordinate, so x1 plus y1 minus 4 times the second coordinate, which is x2 plus y2. Let's now expand it, things where we can. So I'm writing it x1 plus y1 minus, now this is absolute value. We cannot just throw away the absolute value. We cannot take things out of them. If we want, we have to write the absolute function as a piecewise function. But we are not going to do that over here, so we leave it like this. Comma. So here I can distribute the negative 4. So I get x1 plus y1 minus 4x2 minus 4y2. Okay, now we will leave this as it is here and look at the other from the other side. So from the other side, we should have tx plus t of y. So this gives us x1 minus 2 times absolute value of x2, comma, x1 minus 4x2 plus now the y vector. So it will be y1 minus 2 absolute value of y1, comma y2 here, minus 4 y2. Now we add these two vectors. So we get x1 plus y1 minus 2 times absolute of x2 minus 2 times absolute of y2, and then the other component of the vector is x1 minus 4x2 plus y1 minus 4y2. Now when we compare these two results, let's call it 1 and call this a 2. When we compare these two results, so note here, this compare the two, so these are same. If you look at the second piece or the second part, maybe we should look at the next line here. So this is the same, these are the same, but this quantity and this quantity, these are not the same. And the reason is because the absolute value in general, if we have a plus b absolute, that is not equal to absolute of a plus absolute of b. You can check that with different numbers. So that is why these two are not equal, therefore T is not linear. So now that we check this property is not being satisfied, we do not need to check the second property. Okay, let's look at the next example. It says define T from R3 to R3 as T of x1, x2, x3 becomes x1, x2 negative of x3. So this vector is being mapped onto x1, x2, negative x3. So we have to show that T is linear. So again we will use the two parts of the linearity property, and the first one I have to show that T of x plus y is equal to T of x. This is I have to show Tx plus T of y. So note here again we are using the horizontal vector. So x, if x and y are known, then x plus y will be x1 plus y1, comma x2 plus y2, comma x3 plus y3. So the T of x plus y will be, so you can see it will be x1 plus y1 plus, comma x2 y2 plus y2, comma, so the third component gets a negative sign in front. So we have negative of x3 plus y3. We as well just distribute the negative signs. We get negative x3, negative y3. So negative x3 minus y3. Now we can leave it like that and come from the other side with the tx plus ty. So if you want, you can try that, but I will show you this way, that I can think of it as the sum of two vectors with coordinates x1, x2 minus x3 plus the vector y1, y2, negative y3. But what is this one? This is t of x plus, and this is t of y. So first condition is satisfied. Now let us look at the second condition, which is that t of rx should be equal to rt of x. So we start with t of rx. So this will be the vector will have components rx1, rx2, which is then equal to, and rx3, the third component. Let me rewrite this. Okay, so rx2, rx3. So this will be mapped on rx1, rx2, negative rx3. Now we can pull out the r from the vector, and we are left with x1, x2, negative x3. Now note, this thing is just the t of x. So we get r times t of x. And that's what we wanted to get. So yes, we have proved that this is linear. So hence, t is linear. The last problem here says let t be a transform for from Rn to Rm, and let it be a linear transform. And then we have three vectors, and we are given that they are linearly dependent in Rn. So now the question is, explain why the set t of v1, t of v2, and t of v3, which means the images of these vectors in the codomain, why are they linearly dependent? So this is how we can argue. We can know that v1, v2, v3 is a linearly dependent set. What does that mean? It means that if we write a linear combination and set it equal to 0, so if we write c1, v1 plus c2, v2 plus c3, v3 equal to 0, then not all of these CIs, C1, C2, C3 are going to be 0. At least one of them will not be 0. So let's say that C3 is not 0. So if C3 is not 0, then V3 can be written as a linear combination of V1 and V2 as this. So I hope you guys can see how I got that. Keep the C3, V3 here and move the other two terms on the right hand side, and then divide by C3, because we said C3 is not 0. So we can divide by C3. Now, because T is linear, so when I take the T of V3, it will become T of V3 is equal to negative C1 over C3, because this is a scalar, times T of V1 minus C2 over C3, T of V2, which means we are able to write T of V3 as a linear combination of T of V1 and T of V2. So which means the set is not linearly independent, or the set is linearly dependent.